guys, hello everyone. So before just moving onwards to another topic, I just wanted to discuss some important questions, okay, which are based on the metal carbonyls only. All right. So I have given you a lot of examples in the metal carbonyls video, but we want to continue and see what kind of previous year questions are being asked on the same topic. Chalo. So let's start the discussion. So first of all, I'm taking this question over here. Treatment of iron pentacarbonyl with 1,3-butadiene gives B that shows two signals in its proton NMR spectrum. B on treatment with HCl gives C, which shows 4 signal in the proton NMR spectrum. The compound C is. Alright guys, so see, you have to stop the video and try it by yourself, because by now, after watching the video, I think you have enough knowledge to solve this. Also, if you haven't already seen, there's a folder separately practice session karke, practice videos. So that folder has topic wise practice questions of all the topics of organic and inorganic. So please go through them as well. Okay, so yeah, let's continue. First question. So treatment of this iron pentacarbonyl with 1,3-butadiene. So you know that 1,3-butadiene system is like this. It's a diene. So if it is going to like replace carbonyls, तो कितने replace करेगा? Definitely it is going to replace 2 carbonyls. So let's say that these 2 equatorial carbonyls are being replaced like this, neutral compound. Okay. Now this is going to be our B compound. All right. Now that shows 2 signals in the proton NMR spectrum. Why does it show 2 signal? Because even if it is high temperature, low temperature, there's a sigma plane which is passing through the molecule like this. Okay. So that sigma plane is going to give you 2 types of signals only. One is for the methine proton and the second is for the methylene proton B. So there are going to be A and B, 2 different signals which are repeated on this side as well. Okay. So this is B. B on treatment with HCl yields C. So if we react this molecule with HCl, you know, when you are studying a little bit more about the alkenes bound to the metal, you will know how they are going to react. So if there is H plus, so where is the H plus going to coordinate? Definitely the alkene is going to attack over the H plus, but after forming the allyl complex, because you know after it attacks over the H plus, ये हो जाएगा methyl, यहाँ पे आ जाएगा एक positive charge. So this positive charge, the iron is providing electron density to make it the allyl complex, but the iron got the positive charge now. Okay. So iron is coordinatively as well as electronically unsaturated. If you count the electrons over here, this was an 18 electron system. If you count the electrons over here, you have 3 carbonyls. So 6 plus iron, 8 plus 3 for the allyl minus 1. That is going to be how much? This is 16 electron system. So definitely you are going to need 2 more electrons. So कहाँ से आएंगे? Cl minus से आएगा. So after the Cl minus is attacking, the coordination as well as the electronic saturation, both of these are obtained. So you are finally going to get this compound, and the positive charge is also removed. So this is your final product, option number B. Okay, very nice. Let's move onwards to second question. Now the question is asking you the proton NMR spectrum of ruthenium eta4C8H8. This is what? This is cyclooctadiene. And CO whole 3 at 23 degrees centigrade consists of a sharp single line. So at 23, that is like room temperature only one single line it is showing. The number of signals observed at low temperature in its spectrum is. So this question is mostly based on the type of binding and how it is affected on, let's say, higher temperature, lower temperature. Alright, so since we have done some questions on this topic, proton NMR we have seen for organometallic compounds yesterday. That's why we are looking at this question today. So if you can understand, it is eta4 C8H8. What does that mean? C8H8 is what molecule? It is cyclooctatetraene, like this. But only eta4 is connected. That means that 2 of these alkenes are going to be connected to ruthenium, and it is further connected to 3 carbonyls. So when we are taking room temperature, then what happens? It is only showing in the room temperature, it is only showing you one single line. Why is that so? Because it is eta 4 and all of this. There's a concept called ring whizzing, and this concept is very useful when you are talking about the spectrum, because then only you are able to catch this. Okay, catch this phenomenon. What is this phenomenon? It is known as the ring whizzing. What is ring whizzing? It is whizzing around its own axis. That is, if the ruthenium is bound to these 4 carbons, what will happen at room temperature? It is constantly changing like this, घूम रहा है करके, but eta 4 is remaining the same. So what happens is, maybe at one point of time it is bound with these 2 alkenes, but then it is shifting again. So maybe at another point of time it is bound by these 2 alkenes, because eta 4 remains same, but the ring is constantly like rotating. Then these 2 bonds, then these 2 bonds, so it is constantly rotating, and because of that the nature of the hydrogens will keep on remaining the same. You might feel like that these all hydrogens are going to be different, because see, even if you want to have a sigma plane, अगर आपके पास sigma plane भी है, तब भी क्या होगा, you will say that no ma'am, these hydrogens are different. This is, let's say, HA, HB, HC and HD. These are different because you have a sigma plane like this. So these are different, 4 different types of hydrogen, and these 4 are let's say these 4 are same. बट ऐसा नॉर्मल टेम्परेचर पे नहीं होता है. रूम टेम्परेचर पे रिंग विजिंग टेक्स प्लेस. इट्स कॉन्स्टेंटली रोटेटिंग अराउंड the 2 pi bonds. So which 2 pi bonds are connected, we cannot say. At room temperature, either these 2, then these 2, then these 2, then these 2, like that. That's why all the hydrogen becomes the same at room temperature. Okay, but at lower temperature there is no rotation or no whizzing of ring, which means everything is now static. पूरा stop हो गया है. So when everything is static, you can just take that, okay, only 2 of these are going to be bound. तो वहाँ पे कितने proton signals आएंगे? You see A, B, C, D, 4 signals you are going to get. So yes, 4 is the correct answer, because at low temperature it becomes static. Alright, very beautiful question. Alright, another question number 3. Eta 3 C3H5 MnCO4 shows fluxional behavior. Now you know what is fluxionality. The proton NMR spectrum of this compound when it is in the non-fluxional state shows. So either they are asking you fluxional behavior based on the temperature, or they are just directly telling you that this is fluxional, this is not fluxional. ठीक है? तो ये जो change हुआ था अभी, at room temperature, this compound at room temperature is also fluxional. What is fluxional basically? What is fluxional? What is ring whizzing? Fluxional and ring whizzing are almost similar concept. That is, they are constantly changing their geometry. Alright, the molecule is constantly changing. So when we are talking about eta 3 C3H5, what is this system? This is nothing but the allylic system. Alright, and what is this? Let's see. There are 4 carbonyls, and here it is connected in this way. C3 Alright, C3H5. So basically what is happening is you are having a allylic system like this. So this is definitely going to have 1 methine, 2 methylene hydrogen. So total hydrogen 5. So what is fluxional behavior? Just like the previous one, वो तो वहाँ पे ring था, तो ring was whizzing. Here it's not ring, but this is also constantly going to rotate. So that is going to constantly rotate. So I cannot say that these 2 hydrogens are different. They are same. Okay, so at room temperature, this shows fluxional behavior at, let's say, room temperature. ठीक है? Alright, but when it is there in the non-fluxional state मतलब कि it is rigid now. It is no more fluxional, rigid or static, whatever you want to call it. It is fixed. When it is fixed, it is not rotating. Then what is the spectrum? So the proton NMR spectrum of this compound, when it is in the non-fluxional state, shows. So non-fluxional state we know is rigid and static, not moving. So it is going to be basically there are two hydrogens. So see, if it is not moving, then you are going to get one signal for this carbon having two hydrogens. So two for this one, another for this, which is going to be like one, and another for this. So it is going to be 2:2:1. So you are going to get three signals in intensity ratio of 2:2:1 when it is there in the non-fluxional state. Alright, now we move onwards to another example. Heating a sample of eta5C5H5, that is the CP ligand, connected with molybdenum. So you see over here, this question we have done yesterday from BD Gupta, isn't it? And now this question is asked in this way. That's why I tell you that book questions are so important. So you see, this is how the complex is. Alright, because there are 3 carbonyls per molybdenum in this way. Now this results in the formation of this complex where there are only 2 carbonyls per molybdenum. So it could be written as molybdenum triple bond MO. We have already done this question, so I'm not going to explain again and again because it's very simple. So this is how it is going to be. Now the stretching frequency is not given for the carbonyl, so we are just randomly writing it as a terminal carbonyl. Okay, if the stretching frequency was given, then we would actually make it a complex like this, जो हमने कल किया था already. ठीक है, which we have already done. So the bond order actually changes from 1 to 3. This question is already done. It's a very nice question. ये होगा इसका actual structure. If we get the IR value, we will confirm this. So 1, 2, 3 is the correct answer. Okay. Now next question, reaction of sodium. This is another complex which we have got by reduction basically. ये complex कहाँ से आया है guys? Yesterday only we discussed. This comes from Mn2CO10 after the sodium and sodium gives its electron in the presence of ammonia. तो ये reduction से आया है. Now this is reacting with the allyl chloride gives A along with NaCl. So this kind of question also I've told you yesterday in the session. So उसी का हम example देख रहे हैं. MnCO5. Alright, there is a negative charge on this complex. Okay, so I'm just writing the negative on manganese itself because manganese is having the negative charge. When it is attacking this system over here, ये ऐसे attack कर जाएगा. And what is it now? It is MnCO5 and manganese has a direct bond with the allylic system. This is an 18 electron system over here. Very nice. Now photolysis of this compound. Photolysis of the compound A results in a compound B together with elimination of CO. So definitely minus CO उससे क्या हो जाएगा? उससे हो जाएगा it is MnCO4, but that is going to decrease 2 electrons, no? So what happens? There is a change in hapticity and the molecule changes from MnCO5 to whole 4 but eta1 to eta5. So ये जो B हो जाएगा compound, that B compound is going to be like this, eta3. It is not going to be eta1 and dimer it is absolutely not forming. Okay, dimer तो ये break करके आया है already. So this is going to be the correct answer. Alright, next important question. A compound A having the composition FeC9H8O3 shows one signal at 2.5 ppm, another one around 5.0 ppm in its proton NMR spectrum. Alright, so you see the data which is given is of this compound. ठीक है, ये क्या करता है? One signal it is showing at this and another at this in the proton NMR spectrum. The IR spectrum of this compound shows 2 bands, one at this, another at this. So it also follows 18 electron rule. 3 conditions are given. Okay, so you just have to find the correct structure first. If you find the correct structure, तो फिर आप ये बता सकोगे that which ligand is bonded. So just try this out guys, it's very simple. Now it has one signal at 2.5 ppm, that absolutely means it is going to have a methyl, or 5.0 absolutely means it is going to have a CP. तो चलो एक structure बनाने की कोशिश करते हैं that okay it is your eta5 CP connected to iron, but there are how many other ligands which are present. This question also made you do from BD Gupta, has been asked from the back questions. So this is what C5H5 कितना माइनस करना है, इसमें से माइनस करना है C9H8O3 माइनस करो इसको, you will get C4H3O3. What does that mean? That means you are having 3CO plus 1CH3. Just check it once again. यही मिलेगा 3CO and 1CH3. So are we having this 3CO and 1CH3 all of them connected to iron? अगर ऐसा होता तो how many electron it should have? 5 plus 8 plus 6 for the carbonyl plus 1. तो कितने इलेक्ट्रॉन हो गए हैं? 6 and 6 12 plus 8. This is like 20 electron system. Not allowed. 20 electron system not possible. एक और possibility है that if there is a 2 positive charge on this, we can minus 2 electron from here. But the molecule here is not mentioned to be ionic. नहीं तो बोल देते कि ionic compound. It is not an ionic compound. So which means we have one more possibility. What that possibility is like this कि आप CH3 सीधा नहीं लिखकर इसको acyl group बना दो. If that is the case, we must see that this carbonyl frequency should be coming under like the ketone frequency, isn't it? So absolutely you have it. ये देखो, ये जो से ketone की frequency है 1680 metal bound ketone, so it is absolutely 1680 and 1900 is for the terminal 2 carbonyls. Alright, so IR frequency confirms this is the correct structure. Alright, as well as the proton NMR also confirms that the 5.0 is for the CP and methyl is connected to the acyl group and that's why it is 2.5. Okay, अगर directly connected होता metal से तो it should have been like a negative value. Okay, so this is the correct structure. Now, it has a eta 5 CP group, absolutely. It has a terminal carbonyl ligand, yes. It has a methyl ligand, no. It has a iron hydrogen bond, no. So A and B are the only correct answers. ठीक है, तो ये हो गए इसके correct answer, right? Alright. So I guess we come back to this question once because ये जो question है guys, this is a little bit tricky over here. When you are asking the question in the non-fluxional state, that means it is there, it is static. Even in the static conformation, you should have 2:2:1 like this. Static है कोई बात नहीं. It is not moving around. But in the static conformation also you have a sigma plane which you can see. So if we consider the sigma plane, because all the ligands are also same and there the allyl group is like completely symmetrical. अगर propyl होता, अगर एक और methyl लगा होता, we could have thought about it. But it's all symmetrical. That means you can have these two hydrogens and these two hydrogen become the same. And if that happens, you will have two signals in the intensity ratio of 4:1. So I would say that B is the correct answer for this question. Okay. Right, now let's move onwards and study a new topic. So guys, now we are going to move onwards to another topic which is like very simple, and most of the importance of this topic is like knowing examples, about the metal nitrosyl. The maximum type of question that can appear for metal nitrosyl is mostly based on the 18 electron rule, the bent or the linear nitrosyl, only that much. Alright, but still it makes an important topic, so we'll try to know some important points about the metal nitrosyl. So first of all guys, you already have seen that the nitrosyl itself, it has one extra electron than a carbonyl. So it is having a 15 valence electron system. A carbonyl has a 14 electron valence system. Okay? So it also has a bond order of 2.5. Short nitrogen oxygen bond length of 1.15 angstrom and a low dipole moment of 0.15 dBi and a high bond energy of 891 kilojoule per mole. So bond energy is definitely going to be high. Triple bond hai, like almost a triple bond with more electronegative atoms. Now why is the bond order 2.5? We will see very shortly. We expect कि ये तो nitrosyl है, इसका bond order तो 3 होना चाहिए, but it is 2.5. Why is that though? We'll see. So nitrosyl can be a 1 electron or a 3 electron donor. It is very important कि 1 और 3 दोनों behave कर सकता है based on the type of bonding. there are three, we can just replace 2 nitrosyl with 3 carbonyls, because I've already shown you a carbonyl has 2 electrons, so 3 into 2 is 6. Nitrosyl can give you 3 electrons, so 2 into 3 is 6 again. So ये इस तरीके का half substitution करता है. So when nitrosyl acts as a 1 electron donor, it forms a bent complex with an electron pair on nitrogen itself. So when you are actually drawing the nitrogen structure, see, it is how the nitrosyl is written. ये 2 electron जैसे carbonyl लिखते हैं वैसे nitrosyl नहीं लिख सकते. We used to write carbonyl like this. Okay, but we cannot write nitrosyl like this because nitrosyl में 3 electron है. There is an odd electron. That's why the bond order is 2.5. So it can behave, it can donate in 2 different ways. अगर ये एक ही electron donate करता है, if it donates only 1 electron, then it is going to appear like this, that 1 electron is donated to the metal and it is going to be added in a bent manner because the lone pair is still existing on the nitrogen. Okay, but if it is like giving the lone pair as well as that 1 electron, then it is going to appear like this, linear. ठीक है? So bent complex बनाएगा मतलब nitrogen पे electron pair है, it is going to be bent, it is only a 1 electron donor. When it is donating 3 electrons, it is going to form a linear complex altogether. Okay? In ionic or oxidation method, when we are considering the ionic method for counting electrons, we say when the nitrosyl is giving 3 electron, तो उसको हम बोलते हैं NO plus, nitrosyl cation. Okay, because it connects linearly. And when we say it's giving only 1 electron, we say it is NO minus. It connects in a bent manner. क्योंकि आपको पता है Cl minus हम ionic, we usually count in the neutral method, but when you have to take the oxidation or the ionic method, you will say that the Cl minus and NO minus, these are like similar, these are giving you 1 electrons. Okay, so 1 electron donor is count as NO minus. So आप ऐसे confuse मत हो जाना. In different books it is mentioned in a different way. So this nitrosyl itself can behave 2 ways. NO plus gives you 3 electron, NO minus gives you only 1 electron. Okay. Now both the nitrogen and oxygen can become electron donor sites, but nitrogen donates क्योंकि यहाँ पे क्या होता है, डोनेशन के बाद में पॉजिटिव चार्ज आता है, which nitrogen can handle, but oxygen can comparatively is more electronegative, so it can't handle that. ठीक है. Next, nitrosyl can be characterized by IR spectroscopy. These two are the most important thing, IR value and the 18 electron count. बस ये दो ही चीजें आती है. The free nitrosyl IR stretching is around this 1896 centimeter inverse, and free NO plus is 2250 centimeter inverse. Why NO plus is like this or NO is like this? क्योंकि यहाँ पे एक इलेक्ट्रॉन एंटी बॉन्डिंग ऑर्बिटल में है. NO has 1 electron in the anti-bonding orbital, and that's why the bond order of NO is equals to 2.5. But when you are removing this 1 electron, the bond order of NO plus, that is going to become 3. Okay, that's why the stretching frequency increases for NO plus. अब ये तो free nitrosyl की बात हुई, but when the metal is bound to the nitrosyl, what is the frequency? There's a big change. It is going to be around 1600 to 1900 centimeter inverse. Okay, तो ये हो गया है terminal nitrosyl, which is going to be in this range 16 to 1900. ठीक है. Now bridging nitrosyls are also observed just like bridging carbon. ऐसा भी तो हो सकता है ना, that this is giving the lone pair to some metal and the 1 electron to another metal. That is also possible. So bridging nitrosyl is going to have a different range of frequencies, definitely smaller. आप example देख लो इसका. Example number 1. So in this complex, I am having, it's a chromium complex, all right. And guys, you have to like kind of remember these examples. नहीं तो आप भूल जाओगे, एग्जाम में गलती कर दोगे. So you have to remember these. What are these? Okay, I'm writing CPCR NO whole 2 like this, because what is happening over here, अब अगर आपको ये complex दे दिया and they're asking you, oh, what is the nature of the nitrosyl, then what will you answer? You have to know by counting the number of electrons that this CP is giving you 5 electrons. Okay, 5 इलेक्ट्रॉन्स फॉर Cp प्लस क्रोमियम के लिए कितने इलेक्ट्रॉन है? 6 इलेक्ट्रॉन्स फॉर क्रोमियम. 5 electron for Cp, 6 electron for chromium. Now these nitrosyls are behaving two different ways. Okay, एक में हमने ले लिया 3 electron, एक में ले लिया 1 electron. Okay, like this. So if that is happening, what is the electron count? We are not considering the metal-metal bond as of now. So if we don't consider the metal-metal bond, it's 5 plus 6 plus 1 is going to be 12. प्लस 3 इज 15 इलेक्ट्रॉन सिस्टम. तो हमें देखकर ऐसा लगेगा कि मे बी अ क्रोमियम क्रोमियम इज फॉर्मिंग अ ट्रिपल बॉन्ड. व्हाई? बिकॉज यहाँ पे 3 इलेक्ट्रॉन कम है. बट दैट इज एब्सोल्युटली रॉन्ग. इन दिस केस द इलेक्ट्रॉन काउंटिंग इज नॉट गोइंग टू बी लाइक दिस. इसकी इलेक्ट्रॉन काउंटिंग ऐसे नहीं होगी. बिकॉज यू आर गोइंग टू टेक इवन इफ इट इज ब्रिजिंग, लेट्स काउंट कि ये लोन पेयर इधर दे रहा है और एक इलेक्ट्रॉन इधर दे रहा है. And for example, the lone pair over here given to this chromium and 1 electron given to this chromium. So how are we going to count the contribution? Totally, we are going to take 3 electrons. Okay? So Cp, we are having 5 electrons. Chromium, we are having 6 electron. Nitrosyl, in matlab 3 into 2 is 6 once again. That whole multiplied by 2. So how much is this? This is going to be 6 and 6, 12 plus 5, 17 into 2 is 34. Okay. Now if you see how many metal-metal bonds are possible, तो total 2 metal है, तो 36 minus 34 divide by 2, 1 metal-metal bond. This is correct. Okay. So you add 2 electrons for the metal-metal bond. Now it is going to be completely 36 and that is how it follows the 18 electron rule. ठीक है? So the most important thing is electron counting and the type of bonding for nitrosyl. तो nitrosyl जो linear है उसका frequency इसके बीच में आएगा 16 to 1900. That is 1672 centimeter inverse. Okay. The the bridging nitrosyl is very less, 1505. So just remember bridging nitrosyl is around 1500. ठीक है, approximately. You can't remember the exact value, so approximately 1500. Okay. So this example is very important क्योंकि आप electron counting में confuse हो सकते हो. चलो next. Now what happens over here? I have another complex of nitrosyl. Let's say I am just writing the formula because in the exam you'll get the formula, right? आपको वहाँ पे ये नहीं मिलेगा compound का structure. So you have the formula in this way and you have 2 nitrosyls, NO whole 2. So RuCl PPH3 whole 2 NO whole 2. Now count the number of electrons. So you see, if you are counting the electron 8 plus 1 plus 4 for phosphine plus I'm counting, let's say for example I don't know the structure, so I'm counting 3 into 2 6. That is going to give me how much? 8 plus 1 ये हो गया कितना? 10. So it is going to give me 19 electron. Do I want 19 electron? Absolutely not. तो इसमें क्या गड़बड़ है? मुझे कुछ हटाना पड़ेगा इसमें से. 8 plus 1 9 plus 4 is 13 plus 6 is 19. I want to remove some electrons from here. What am I going to do? I am going to make one of the nitrosyls to be bent. And if I say that एक electron count करेंगे फिर उसके लिए. So let's do it. Ruthenium again 8, then 1 for chlorine, then 4 for the phosphine, then 3 for 1 nitrosyl and another nitrosyl only 1 electron donor. ठीक है? That is going to give me how much? 4 plus 4 8, 8 and 8 16, 117. Yes guys, this is a 17 electron system. So you have to remember this example, okay? Don't like fall into the trap in the exam. This is a 17 electron system which is found to have one linear and one bent nitrosyl. तो linear वाले की value यहीं आ रही है इन दोनों के बीच में 1845 centimeter inverse and the bent nitrosyl is 1687 centimeter inverse. Okay, very important. Now the next one over here. You are having a Cp 5 electrons plus nickel has 10 plus nitrosyl has 3. So this is simple 18 electron system. No problem, no trouble. Linear nitrosyl है, ये value आ गई. Okay. This one, what is this? It looks like कि ये जो Vasca's complex था उस पे nitrosyl लगा दिया. So you might be tempted because Vasca's complex you know. that if I write the formula of Vasca's complex, you know it is a 16 electron species, isn't it? सबको पता है Vasca's complex क्या? This is a Vasca's complex. It's a 16 electron species. Now, if you think कि you are going to, you don't know the structure, you still don't know the structure. Let's say I'm just giving you the formula. एक CO तो था ही, अब एक NO भी आ गया है, and a positive charge. You might be tempted to count the electron like this: 9 plus 1 plus 4 plus 2 for the carbonyl plus 3 for the nitrosyl, because हम सबसे पहले यही करते हैं, -1. This is how you are doing it. 9 9 plus 1 is 10. अब ये कितना आ जाएगा? 4 plus 2 plus 2 is 8. तो ये हो जाएगा 18 electron system. You might be very tempted to do this because you know 18 electron system is very stable. ठीक है ना? आप ये कर दोगे, पर ये गलत है. This is wrong once again. So I'm just mentioning this like this. This is wrong. Why is it wrong? Because this nitrosyl is not linear. आप हमेशा 18 इलेक्ट्रॉन काउंट करके नहीं बता सकते. So how are you rather going to count? You are going to count like this: 9 plus 1 plus 4 plus 2 plus only 1 electron for the nitrosyl minus 1 electron for the negative charge, for the positive charge. It is still going to be a 16 electron system. How important is this? Because guys, when the nitrosyl connects to the Vasca's complex, it is going to connect into the bent manner. Okay, and you have to know this. ये आप एग्जाम में calculate नहीं कर सकते हो, because you will calculate wrong. So you have to remember this, that Vasca's complex still gives you a 16 electron system which is square pyramidal in shape, and it has a bent nitrosyl, just like this one. Okay, this is also square pyramidal in shape and bent, and it is a 17 electron system. This one is a 16 electron system. All these examples have to be remembered. ठीक है, आगे चलते हैं. Now, what are some important points about the nitrosyl compound? The IR spectroscopy and EPR spectroscopy can be used to distinguish between the different modes of binding. IR spectroscopy का हमने देख लिया, because the terminal and the bent, they are going to, even the bent and the bridging one, all of these are going to show you different frequencies. Got it? So very clearly you can explain based on the IR spectroscopy. What about the EPR spectroscopy? Do you remember the concept? I have already taught you in the organic, while we are studying organic spectroscopy, we have discussed EPR. Whenever you are having an odd electron, जब भी आपके पास odd electron होता है, you can find out EPR for that molecule. So when it is bound in a NO plus manner, मतलब कि all the 3 electrons are lost. So this is not having no odd electron. But when it is bent in the NO minus way, that is, it's there in the bent fashion, then it has 1 electron odd. Okay, it's only a 1 electron donor. So इसीलिए आपको EPR से भी पता चलता है NO के बारे में. Now, linear MNO groups. Yeah, they show you a triple bond like this. Okay, and they absorb in this range. 1650 समझ लो या 1600 समझ लो to 1900. Just remember it like this. Okay. Now we have some more example. As many examples you can go through, उतने ही ज़्यादा अच्छे होंगे, exam में problem नहीं होगी. So what is this? Iron penta cyano-nitrosyl complex. Here it is linear, and that's why look at the frequency, very high. Why is the frequency of nitrosyl very high? Because on the other side of nitrosyl, ये देखो, just like it is the concept of carbonyl only, you have 5 nitrosyl over here. Sorry, 5 cyanide groups over here and 1 nitrosyl. So if there are like electron donors, if they are like pushing electrons to iron, all the electron will go into nitrosyl, because this is also a pi acceptor. Okay, but here all the ligands are strong pi acceptor. That's why not much electron density go to the nitrosyl, and that is why what happens, इसकी जो bond order है, that remains as a triple bond. It remains as a triple bond over here. Okay, because the other side the pi acceptors are present. That's why the frequency is so high as compared to these. क्योंकि यहाँ पे क्या है, ये भी donors है, ये भी donors है, सभी donors है. See, this is a donor. That's why the frequencies are so low over here. Okay, next. Again, cyanide example. So this is a 3- charge on the metal. Metal has a 3- charge. but still there are so many good pi acceptors कि वही ले लेते हैं, and because yeah there is a difference in the charge, that's why there is a difference in the frequency also. Now what about the bent nitrosyl? The NO double bond is going to absorb. देखो जब linear होता है तो NO triple bond होता है, but when it is bent it is going to only have a double bond. That's why the frequency is low. So in this range it is going to absorb like this. For example, in this way. So what is happening? There is a cobalt. You are having like 5 amine groups and 1 nitrosyl. Okay, and 1 nitrosyl, which is going to be bent in this way. Alright, there is a 2 positive. Now we should always calculate the electrons. कितने electrons है ये? Cobalt के पास में 9 electron plus 5 into 2 for the ammonia, 10 electrons from ammonia. Nitrosyl से कितने electron आने चाहिए? Only 1 if it is bent, minus 2 for the plus charge. So how much is this? It is going to be an 18 electron stable system, octahedral geometry. Alright, so these are the most important things about the nitrosyl. So let's also understand that why the nitrosyl is having a bond order of 2.5 and why NO plus has a bond order of 3.0. So let's see guys, nitrogen has how many electrons? 5 electrons, and oxygen has 6 electrons. So when they are filling up all the electrons over here, you see that 2s and 2s are going to form the sigma 2s and sigma 2s star. Alright, electrons are filled equally. So ये हो गया है यहाँ पे complete electron contribution of the 2s. When we move onwards to the higher energy 2p, we see that 3 electrons from the 2p and 4 electrons from the 2p of oxygen are going to be filled up like this. First into the sigma 2p, then comes pi, because the Z value is now greater than 14. Okay, it's 15, so it is sigma below. Then comes pi, then comes pi star. So when we are filling the electron, ये 7 electron हो जाते हैं total. There is one extra electron. That extra electron goes into pi 2p star. So when we are counting the bond order of the NO simply, yeah, you're going to take 6 electrons of bonding minus 1 electron of anti-bonding divided by 2. That is going to be equals to 2.5. Alright, and when you remove this 1 electron from the anti-bonding orbital, so when we are taking NO plus, the bond order is going to be is equals to 6 minus 0 divided by 2. That's equals to 3. Alright, so this extra electron which is present, because of this odd electron, the simple neutral NO molecule is EPR active, because EPR molecules, only those molecules which are having an odd electron or basically one unpaired electron, they are showing the electronic paramagnetic resonance. Okay, so NO molecule is paramagnetic in nature. Okay, chalo. So now we move onwards about, we see some more examples of bent nitrosyl complexes. Okay. तो ये देखते हैं guys. First of all, we have already seen this complex of the cobalt 2 plus, where nitrosyl is bent because it is having a lone pair like this, only 1 electron donation. Another compound over here. Again, see the central atom is the same over here, just that. Then CS is a minus, it's a negative ligand, and there is an overall positive charge on the complex. So oxidation state must be 3 plus for cobalt. Here also it is 3 plus. Right. So if you count the number of electrons, it is going to be the same 18 electron system. This is like diars. You already know what is diars now. And again, it's a bent nitrosyl. Okay, only 1 electron donation required. So next example, you see we have taken a azide also. See, this is an azide. 1 electron for azide. Nickel is having like 10 electrons plus 4 electron from 2 of these phosphanes. Now what is the electron donation of the nitrosyl? If we take 1, then it is going to be how many electrons? 16 electron system. So guys, it is possible that it's not always necessary कि nitrosyl electron donate करके 18 electron compound ही बनाएगा. Not necessary. It is you have to like take note of these examples where nickel, which is a D8 system, can also form a tetrahedral stable complex with bent nitrosyl. ठीक है? Be careful about this. Then again, this one we have already seen Vasca's complex. We have also seen this one again. Both of these are similar. ये क्या है? ये 16 electron species है और ये कितना है? ये 17 electron species है. Okay, one nitrosyl is linear. Count the electrons: 8 plus 3 for this plus 4 for the phosphine, 1 for the chlorine plus 1 for the nitrosyl over here minus 1 for the positive charge. कितने हो गए? ये दोनों cancel हो जाएंगे. You are having 16 electrons. Okay, so in this one you are having 16 electrons. 8 plus 4, 12 plus 15 and 16. Yes, 16 electron system. Both of these are basically the same. Alright, so yeah. ये हो गया फिर से 16 electron system. And they both have been asked in your CSIRNET exam. So be careful, right? Just take note of all of these examples. Next, this one you see again the cobalt is now having a square pyramidal geometry because of these bidentate ligands, and it is again having a bent nitrosyl. Okay, so what kind of an electron donor is this? What is this? This is like looking like a thiourea or something, but it is not. It is like this, S minus and minus. So 2 electron donor it is. Okay, so यहाँ से हो जाएगा 2 electron donor, again 2 electron donor. So 2 plus 2 is 4 plus carbonyl, a cobalt has 9 electrons plus 1 electron over here. So this is it's like a 14 electron system, but anyways, it is stable like this, taking the nitrosyl as a 1 electron donor. Now we move onwards, or let me just see one more thing over here, because I think ki nitrogen pe positive charge hai, so it is NMe2C double bond S minus. Yeah, it is a donor like this, ताकि ये इस तरीके से donate कर सके. All right. So this is basically pi electron, pi to sigma. Yes. All right. This should be a 16 electron system, not 14. Okay, because it is donating from this electron density. So ये 16 electron system ही होगा, not 14. आगे चलते हैं guys. Now here we see some nomenclature, some types of structure and examples. See why we are not going much into detail about nitrosyl, because this much is good enough for nitrosyl for your CSIRNET as well as GATE examination. ठीक है, तो ये देखो structure, linear structure, you have already seen plenty of examples. This is one more. Bent structure, you have seen plenty of examples. Two-fold bridging. Now these bridging are important because इसके तो आपने बहुत example देख लिए हैं. Two-fold bridging में ये देखो, when two metals are connected, see the example over here, Cp2 Mn2, so that with each Mn there is going to be a Cp like this. There is mu NO2, दो nitrosyl bridges है, one bridging, another bridging, and two simple nitrosyls. Now the question may be like this: how many metal-metal bonds are present? Because you have to find the proper structure. तो कितने metal-metal bond present हो सकते हैं? Let's see. Count the number of electrons on this manganese. That is 7 electron on the manganese, 5 from the Cp. Let's say 3 from this nitrosyl over here. Okay, so how many electrons are these? These are going to be 15 electrons. It needs 3 more electrons for 18. So it is absolutely going to get 3 electrons from any one of the nitrosyl. So there is no metal-metal bond required. Okay, this is going to be the structure. Similarly, a three-fold bridging. So you have Cp3CO3 mu3NO2. How could be the structure of this complex? Guys, you can very easily find out because you have already seen a similar structure like this. जब हम isolobal analogy पढ़ रहे थे, then you have studied this thing. One nitrosyl bridging all the metals, and there is another nitrosyl which is bridging all the metals. Doesn't it look like a trigonal bipyramidal system where nitrosyl are taking 2 of the vertices? Absolutely it is. And there are going to be Cp with each of the cobalt. So the structure determination thing is very interesting. ठीक है? Dihaptonitrosyl, see sodium nitroprusside solution. This is very important because इसका test भी आता है. So it is basically what you are having a nitrosyl which is basically dihapto, so connected to both the iron which are present. Okay, so this is important, just take care of this. Sodium nitroprusside dihapto का मतलब क्या होता है, that from both the nitrogen and oxygen it is bound with iron. This is the type of bonding I want you to understand. Alright, next, linear isonitrosyl, that is connected from the oxygen side. It's very rare, so you just have only one example, BRON. Okay, or you can also write it as NOBR, because in your exam it is written as NOBR. It has been asked already. जब NOBR किसी से react करता है तो it breaks down into NO positive and BR negative. ठीक है, remember this. Isonitrosyl bridges. So what are these? These are nothing but the bridges between the oxygen and nitrogen. Both of these are like coordinating to metal. So sodium nitroprusside metastable state. Okay, so that much detail you don't have to remember. Just remember this thing, that sodium nitroprusside is actually having a nitrogen oxygen dihaptonitrosyl bridge like this. ठीक है, चलो. We see a question from June 2014. Yeah, it's an old question, but it's still relevant. Reaction of nitrosyl tetrafluoroborate to Vasca's complex gives the complex A with the MNO bond angle 124 degrees. The complex A and its nitrogen stretching frequency are respectively. So just stop the video, try doing this by yourself. So it's asking about nitrosyl tetrafluoroborate. This is it. Vasca's complex क्या होगा? Iridium connected to two phosphines which are trans to each other. Then comes the chlorine and then comes the carbonyl. This is our Vasca's complex. Iridium is present in +1 oxidation state. अब ये nitrosyl से bind करेगा तो कैसे करेगा? You already know this because we have seen plenty of examples. That Vasca's complex is only going to remain as a 16 electron species only. अगर ये bind करता भी है nitrosyl को तो ऐसे bind करेगा in a bent manner and still has a positive charge. So it is a 16 electron species only. So nitrogen is bound in a bent manner and which is also confirmed by this bond angle. Metal, nitrogen, oxygen. This angle is 124 degree. अगर ये angle नहीं भी बताता तो भी आपको पता होना चाहिए. You should remember the example that it is going to be connected in a bent manner. Okay, so what is the frequency of the bend? It is absolutely not so high, not so high. It is going to be lower, around 1520 or something, or around 1620. लेकिन आपको ये भी देखना है how many nitrosyls are connected. Only one. So only one nitrosyl will be connected, not two. This is wrong. Only A is the correct answer. Very simple.